Hi, we're going to look at the Exam 3 topic list, and we're also going to have a chance to try some more practice problems. So the topics that we're going to cover is everything since we finished Exam 2. So we need to talk about or review integer multiplication and division, and then how we started learning about the rational number system. And then we did all the operations on them. We added, subtracted, multiply, and divided. So that was with fractions. Then we used proportional reasoning to solve some problems, and then that brought us into the different types of decimals, which were terminating and repeating, and then we also did operations on those. Then we learned how to talk about percents, and that finally led us to our real number system. So be sure to review all of your handouts that we've gone over in all of those lecture videos, as well as all of our homework sets from the book in order to prepare. You should be able to do all of those problems by yourself. So I just created 20 other problems just to kind of give you even more practice. So here we go. We need to use a number line and chip model and pattern to show 3 times negative 2. So the very first one, we're talking about a number line. So that's our first way. So if I draw a number line, and I have a 0 here. Well, let's see. Let's make it in the middle since we're talking about integers. We'll put 0 in the middle. And so we need 3 sets of negative 2, which that's going backwards. So we're going to have 3 sets of negative 2, which will end up putting us at a negative 6. So we know the answer to this is supposed to be negative 6. Now with our little chips, we could say, okay, again, 3 sets of negative 2. So negative 2, negative 2, negative 2. And again, you can see negative 6. Now by patterns, that's looking at things that we already know. So we've talked about whole numbers. So we already know like 3 times 3 is 9. We know that 3 times 2 is 6. And we know that 3 times 1 is 3. And so each time you're minusing 3. 3 times 0 then would become a 0. 3 times negative 1, if we're going to minus 3, then 0 minus 3 will be a negative 3. And then 3 times negative 2 will be negative 6. So that's using our patterns. So we're going to do that again with, this time we have negative 3 times negative 2. So for this one, we're going to read this as like the opposite of 3 sets of negative 2. So on a number line, we're saying, okay, well, we already know 3 sets of negative 2. We just did that up above, 3 sets of negative 2. And it wants the opposite of that. So that puts us on the opposite side, which puts us at positive 6. With the chip model, we're seeing that negative as a remove. So if we're going to remove 3 sets of negative 2, we need to have some negative 2's in there. So 3 sets of negative 2, but we really need to start with a 0. So I'm going to make sure that this is really 0. There we go. So it's all even. And so if we're going to remove 3 sets of negative 2, we're going to take all those, remove them. All that we have left is 6 positives. Again, with the patterns, if we look at, let's write this out here. We have 3 times negative 2. So we can see already from above that that was 3 sets of negative 2. So we got negative 6, 3, not 3, hold on. Let's change this up a little bit. So then 2 sets of negative 2 would be negative 4. 1 set of negative 2 would be negative 2. So you can see these numbers, the pattern is that it's decreasing. So 3, 2, 1, 0, negative 1, negative 2. All of these are times negative 2 this time around. And so let's see what's happening on the right side. Our answers, they're all plusing 2. Plusing 2. So 0 times negative 2 is 0 like we'd expect, and you can see it's still continuing that plus 2. So if we continue that on, we'll get 0, 2, and 4. And the last one, negative 3 times negative 2, we'll get a positive 6. Again, that's plusing 2 every time. That's by pattern. Okay, we're going to skip down to part D for a minute. And this one, it has, we have 6 negative, and we want to divide that by negative 2. And so if we do it with the chip model, we start by having our 6 negatives. Let's see, 3, 4, 5, 6. And so to divide by negative 2 means we want to see how many groups of -2 there are. So -2 is what has to be in our group. So here's -2, here's -2, here's -2. So that took 3 groups. Okay, so for the patterns, we're going to kind of steal from part C, even though we didn't do it just yet. But if we have something like 4 divided by -2, we know that that will be a -2. And really this is by checking. What I mean by check, it's that relationship between multiplication and division. So if we have a -2 as our answer, the definition of division says that we should be able to multiply by the divisor to make our dividend. So -2 times -2, we already talked about that will become a +4. So then we can keep going and say, okay, well, then what about if we have 2 divided by -2? Well, that's -1. 2 divided by, let's see, 2 divided by -2. Oops, we just did that. 0 then. Divided by -2, that's just 0. But you can see that each of our values here are decreasing by 1. And each of these guys is decreasing by 2. So then our next guy would end up being a -2 here, divided by -2. And so if we're subtracting, we're not subtracting, decreasing by 1. We're decreasing, it looks like, but because it's negativity, it's actually adding 1. So if we take -2 plus 1, it makes -1. And then if we plus 1, that makes 0. So if we plus 1, then we're going to get a 1. So you can see -2 divided by -2 is 1. And let's try that one more time. So -4 divided by -2. That's going to be, if we, again, add 1 here, that'll make 2. And we could do our check to verify as well. 0 times -2 is 0. 1 times -2 is -2. 2 times -2 is -4. And then going back to our number line, if we have -6 on here, we're kind of doing the same thing. How many groups of -2 are there? Well, there's 1, 2, and 3. Again, I should have went from this direction, but it takes 3 in order to make it to that -6. So then if we go back to part C, I don't think we actually did this one with any chips in our class, but the idea is still, okay, you start with, we have these positives, 3, 4, 5, 6, and so we can't talk about it as groups of -2, or -2 can be the size of our groups, but we do see that there are 3 things in here. And so knowing that there are 3 things and we need the opposite sign, we're going to say this will be equal to -3 then. Similar for our number line, it doesn't really make that much sense to have the 6 divided by -2, so we're going to kind of have to do the opposite. So if we're going to talk about going from 0 to 6, ignoring the sign for a minute, we're going to go, there's a group of 2, a group of 2, and then a group of 2, but we need the opposites, so that's why we're going to say that it's still -3. And then following with the pattern, which I'm a little bit out of room for this guy. So for the pattern for this guy, I guess it could actually be this one, but we could start in the reverse way. So if we already start with the negatives and then go the other way, we could use the patterns that way. Okay, so you should be able to know a few different representations using either the number line, chip model, or patterns in order to show these different products and quotients. For number 2, we want to see why is 2/3 equivalent to 4/6. So if we're going to use pictures for this, 2/3, we need thirds, so we have 2/3 going on here. So if we want to make 6, all of these pieces have to divide up into 2 equal pieces. So you can see that's a total of 6, but really there's 1, 2, 3, 4 parts being shaded. So we just showed that 2/3 was equal to 4/6. For part 3, you want to write 3 equivalent fractions for each. There's lots of different answers that you could have on this one. I'd really start by just doubling because I like to double. So I know that 4 times 2 should be over 5 times 2. As long as these numbers are the same, we're creating a new fraction. So we have 8/10 is equivalent. We can even double again. That's 16/20. And double again, that's 32/40, or you can do some other variation as long as it is equivalent. And so equivalent, we should be able to look at the fraction and kind of cancel out a common factor. So like 32 over 40, I know that this is going to be 8 times 4 over 8 times 5. So you should be able to see the matching factors, and then that way we know that this is equivalent to 4/5. So a over 3, I can still do the doubling, but because we have the variable a, maybe it's nicer just to, let's try multiply by 2 on the top and bottom. That's 2a over 6. Multiply by 3, that's 3a over 9. And then one more, how about multiply by 4? That would be 4a over 12. Those are also all equivalent to a over 3. All right, skipping over to number 4, we're going to use rectangles this time to show. So my rectangles, again, they have to be the same exact size. So if I'm going to draw 1/4 in here, try as best you can to make these guys equal. So there's my 1/4, but if I'm going to draw a third, I should draw a rectangle about the same exact size, so that way my holes and my portions I'm talking about are the same. So 1/3, we have this guy. So then the relationship I see between the 4 and the 3 is really a 12, but that could come from breaking each of these first rectangles into 3 equal pieces. And so if I'm going to break all 4 of those into 3 equal pieces, those are 12ths now, and I have 3 12ths. Similarly, with the thirds, if I break those up into 4ths, I'm going to now have a total of 12 pieces. And, oopsie, this first little portion here, so that was 1/3, is going to be now 4 12ths. So if I add all of these pieces together, I have 1, 2, 3, 4, 5, 6, 7. So I have 7 of these 12ths. Now to draw a picture with multiplication, I really only need one rectangle here. And I'm going to break it up so I can look at the 4ths. So 1/4 is here, and I want to take 1/3 of that. So I'm going to go the other direction, break that up into 3 slices, and I only want 1/3 really. I can go all the way through just so I can see the whole broken up in that way, but I really want just 1/3 of the 4ths, so you can see it's going to be that portion, which is 1 out of, but by extending the lines I can see how many equal pieces I have, which is 12. So again, we were like 4 spaces this way and 3 spaces this way. That's why that became a 12, and then only 1 block got filled. So my final answer is 1/12. So again, a reminder about why we need to have a common denominator when we add is because we must have the same size pieces, because we're adding those parts together. When we multiply, we're just taking a portion of something that already exists. So you can see up here, there was no need for our denominator to be the same because you're just taking a portion of some other part. All right, for number 5, we want to show that 2 1/5 is equal to 11/5. So I'm going to draw my 2 holes. I'll draw rectangles this time here. So there's 2, and then 1/5. So break this up into 5 equal pieces. I need 4 lines. There we go. So there's my 1/5. Be sure to label all your pictures that you're drawing. So there's a hole, and there's a hole. And so we want to show that this is equal to 11/5. Well, within each hole, you have 5 parts. So there's 5/5, and then we have another 5/5, and then we have a 1/5. So altogether, you can see that there are 11/5. To use the distributive property for number 6, we can rewrite 2 1/3 as 2 plus 1/3. And so we're multiplying that times 3 1/2 is 3 holes plus a half. So to distribute, we're going to do the holes multiplied, so 2 times 3. But then we're also going to multiply 2 times the half. And then we're going to multiply 1/3 times the 3. And lastly, 1/3 times the 1/2. And so then that ends up being 6 plus 2/3 plus 1/3 times 3 is 1 whole, and 1/3 times a half is a 1/6. So then altogether we have 7 wholes plus, now the 2/3 and 1/6 needs to combine together, but 2/3 is really equivalent to 4/6. So if we combine the fraction part, we're saying that this is going to be 7 and 5/6. Okay, so now that's using the distributive property. Another common way, which you should be able to do as well, is actually multiply 2 1/3 times 3 1/2 by writing them as improper fractions. So if I write them as improper fractions, just to see that it's the same, this is going to be equal to, well, if there's 2 wholes, that's going to be 6 pieces there plus the 1. We have 7/3 times. Here we have 3 wholes, and if we're talking about halves this time, that would be 6 halves. Plus 1, we have 7 halves. So this will be equal to 49/6. Now 6 goes into 49. Let's see, a few times here. It goes 8 times, and that'd be 48, so 1/6 left over. Now, these are supposed to match each other, so looking back, I made a mistake. I see it. When I multiplied 2 times 3, that was perfect. When I multiplied 2 times 1/2, for some reason I wrote 1/3 here, so this should have been 1/2. So this should have actually been, and this makes the problem actually easier. So we're going to cross this off. So I have, when I do 2 times 1/2, this is 2 times 1/2. This turns into a 1, really. So I have 6 plus 1 plus 1, that's 6, 7, 8, and 1/6, which does match what we had previously. So just be careful with your writing there. All right, so show how you can mentally find, a little cut off here, 3 1/2 times 6. So really it's using the distributive property because 3 1/2 really is 3 plus 1/2. So what I want to find out is what 3 times 6 is, so I can do that in my head, that's 18. And then what's half of 6? That's 3. So 21 is how I would calculate that mentally. For number 8, we need to solve for our x. So we need to get rid of all the stuff that's next to it. So we're going to subtract the 5 6 first, so those will reduce or go away. We have negative 2/3 x. Now, in order for these two fractions here to subtract, they must have a common denominator. So between 4 and 6, they have a common multiple of 12. So I'm going to multiply here, top and bottom, by 3. So I'm talking about 9/12 minus, these guys multiply by 2. That's 10/12. So 9/12 minus 10/12 is equal to negative 1/12. Now, if I want to get rid of the negative 2/3, that's multiplying by x, I'm going to multiply by its inverse, or reciprocal, and I have to do that on both sides. So that's 3 over negative 2. So that's going to be x equals whatever negative 1/12 times 3 over negative 2 is. Well, that's going to be negative 3 over negative 24, which, because those are both negative, we know we'll end up with a positive result. So positive 3 over 24, but then both those numbers have a 3 in it, so it will reduce to 1 over 8. So x is 1 over 8. All right, for number 9, we want to prove why when we take 1/2 and divide by 1/3, we can actually rewrite it as this multiplication by the reciprocal. Now, we showed a couple of different ways you could do this in class. I'm going to show it by rewriting it as one big fraction. So what I mean is I'm going to write 1/2 divided by 1/3. And we just talked about in the previous problem that when you multiply by the reciprocal, it becomes a 1. So if I do that on the top and bottom of this fraction, which I can do, because as long as it's to the top and bottom, it's equal, the bottom becomes just 1, and the top becomes 1/2 times 3 over 1. So really this is just the problem, 1/2 times 3 over 1. So that's one way to do it, and again, there was another way that we did in class as well that you could do. For number 10, we're using the bar model to solve. So we're looking at the ratio of men to women as being 5 to 7, and there are 20 more women than men. So we're having our men being 5, so I'm going to break this up into 5 sections, and then the women is more. It's the ratio is 5 to 7, so I'm going to put 2 more bricks on there. And it says that it's by 20 more. So these two together have to be the 20. So really I could say those are 10. So really each of these little rectangles is worth 10. So when it says how many total people there were, well, there's going to be 50 men and a total of 20 women. So altogether, we have 70 people here. All right, flipping over to the next one, we have Anne, Doug, and Benny. They have candies in the ratio 4, 5, and 7. So we're going to do the same kind of situation again. So we have the 4 and then the 5. So it'll be one more here. And then 7. We got 2 more little rectangles. So there should be a total of 7 going on here. Trying to line them up so I can see them better. So this is Anne, Doug, and Benny. Those are their ratios. Now Benny has 21 more candies than Anne. So let's look at Anne stops right here. Benny stops right here. So you can see that there's these 3 spaces. That's the 21 more that Benny has. So that's going to be, if the 3 equal spaces, that's going to be 7 and 7 and 7. So what I know right now is each rectangle is 7. So Anne then would have 7 times 4, so she's going to have 28. And Doug will have 7 times 5, so he'll have 35. And then Benny has 7 times 7, so she's going to have 49, which again you can see is 21 more than what Anne has, so it checks out. For number 11, we want to write the following as fractions, basically. So we have a whole bunch of decimals. Reminder that these guys are called terminating. And the last 2 guys here, these are the repeating decimals. So 2.83 is going to be equal to 2 83 hundredths, which 83 hundredths can't reduce, but it does want it in the fraction form a over b, so I'm going to write this as improper fraction then. So that's going to be 283 over 100. The next one we have 34, and this time it's 176 thousandths. So write that out of 1,000. And we can reduce the fraction first. So 176 can divide by, let's see, 176 divided by 2 becomes 88. I can actually divide by 4. 176 divided by 4 is 44. 1,000 divided by 4 is 250. So I can actually simplify more. So if I divide by 4 again, that's going to be 11. 250 divided by 4. Nope, that can't work. By 2 then. By 2, that's what it would have to be. So let's go back a second. Dividing by 2, that would be 22 over 125. And as an improper fraction, if I take 125 times the 34, that'll be 4250 plus the 22 there. That's 4272 over 125, which can't reduce because 125 has 5s in it and 4272 does not. Now 0.7 bar, that's the 7 repeated. So in order to do that one, I need to get rid of that repetition. So I'm going to let the repetition be that 0.7 bar. And so that means that 10 times the n would be 7.7 bar. So if I want to take off the 0.7 bar to make it nice and whole there, I need to subtract off, well, that's really n, to keep my equation balanced. So then we're going to have 9n equals 7. Divide by 9, we get n equals 7/9. And you could check that on your calculator, that if you take 7 divided by 9, it ends at 0.77777. So we got our fraction. We're going to do something similar for part D, but this time our n, we have an extra decimal here. That's in the hundredths place. So when we talk about moving it over, we're going to talk about 100n, and that's going to be equal to 6.6 bar. Now what we want to take away is the 0.6 bar, so I'm going to take away 0.6 bar, but 0.6 bar is an n this time. It's going to be 10n. So we're going to get 90n equals 6. Divide by 90. And so we can reduce that fraction if we divide by, let's see, 2. That would become a 3 over 45, which I guess I can reduce by 3 then. That's actually 1 over 15. And so if you check on your calculator, 1 divided by 15, you'll get 0.0666. So we showed right here that this is 0.06 bar, but we actually wanted 0.026 bar. So the 2 doesn't have, let me erase that a little bit. The 2's not repeated, only the 6's. So we still need to take the 0.2, which is 2/10, and add that in here. So we're looking at 1 over 15 plus 2 over 10, which will be equal to, the least common multiple with 15 and 10 is 30. So this will multiply by 2, and this will multiply by 3. So we're going to get 2/30 plus 6/30, which is 8/30. We could reduce that by 2, that will be 4 over 15. So if we take 4 divided by 15 now, that will be 0.26666 repeated. And we got it. All right, for number 12, we want to use decimal grids to find the following. So we have 0.25. I'm going to write that in here. So we have 2/10, and then we have 5/100. And then it wants us to add to that 31/100. That's 3/10, and then one little guy. So then overall, if you look at our tenths, we have 5 of them. 4, 5, and then our little hundredths, we have a total of 6. So we're going to add those guys, 1, 2, 3, 4, 5, 6 together. So the answer to our question is 0.56 or 56/100. For the multiplication, we have 7/10. So let's mark that. Let's just go back to our highlighter. So 7, 1, 2, 3, 4, 5, 6, 7/100 by 6. So we want 6/100 of that. 6/10, 7/10 and 6/10. 4, 5, 6. So then you can see their overlap is right here, all that portion, which is going to be a total of, well, it was 0.7, 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6. And we end up then with 42 of those little guys. So you can write as 42/100 because we're getting used to writing our fractions, but then as a decimal, it would be written 0.42. Now 1.5, if we're looking at that, that just means that we have one whole and then we have 5/10 of another whole. And so altogether here, this is what we're talking about, 1.5. Now we want to take 0.5 of that, or half of that, or 5/10 of that. So we're going to go, again, the other way. 1, 2, 3, 4, 5. So we have 5/10 that way. So then the overlap, you can see, is all of this section here. That's what we're talking about. So if we combine those guys together, it looks like we're going to have, really it's like 15 times 5, which will end up being 7/500, or as a decimal, 0.75. All right, for the next one, our 100 grid disappeared. Must be on the next page. Yep. So let's rewrite the problem. 0.27 divided by 0.03. So what that's saying is that we have 27/100. So we'll draw that. So 27/100. And what we want to do is see how many groups of this guy are in there. So those are hundreds. So I have to look and see, okay, there's one of those guys. There's another one of those guys. Another one of those. I'm doing 3 at a time. So those guys. And then I have to count how many there are of that. 3. I'm off a little bit. Let's see. There's another guy. And then there's one more. So it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of those guys in there. So this will be equal to 9. Now if I want to check that I'm right, I'm thinking about, well, 9 times 0.03 is 9 times 300, which will be 27/100, or 0.27, the same thing. Because remember that this is telling me how many decimal places I should have, so really it's 9 times 3, which is 27, but then 2 decimal places. So either way you want to think about that. For the last one, we're going back to just a subtraction problem. And so if we have 56/100 to start with, so that's 5 of the tenths, 4, 5, 1, 2, 3, 4, 5, 6 of those, we want to take off. So I'm going to cross them off. 1, 2, 3, 4 of those and one little guy. And so what's that going to leave? Well, we already have one row, like this guy could come over. So that's going to be 1/10, and then 1, 2, 3, 4, 5. So we're talking about 15/100ths would be left. For number 13, it wants us to write the decimals as fractions and multiply. And again, this is really getting you to see the pattern of how we're going to actually, or how we have been multiplying decimals. So you might say, oh, well, I know if I multiply 0.3 times 0.4, really that's just 3 times 4, which is 12. And then there's one decimal place, so 2 decimal places. So really it's 12/100ths. So let's see why, again, that happens. So that's 3/10 times 4/10. Well, that's 12. That's the 12 that we're talking about. But now we're out of hundredths. So you can see the 2 decimal places needed there. We have 13 times 2/100ths. Again, it's really 13 times 2, so we get 26. These are 26/100ths, so 0.26. And you can check all of these with your calculator. So we have 2/10 times 3/100ths, so that would be 6 thousandths, which is 0.10 thousandths. So you can see the 3 decimal places. And again, let's see, this time though, it's hundredths times hundredths. And so we're going to have 6, but this time it's 10 thousandths, so we get 1 extra decimal place in there. And the last one, 2 thousandths now, times 3/100ths. We're going to get 6 hundred thousandths, so 0.123, so tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. Lots of decimal places there. All right, on number 14, we want to show why this is actually going to come out to be a repeated decimal. So we're going to do our division, 2 divided by 11. Now that can't divide because 2 is smaller than 11. So let's look at these as tenths. We have 20 tenths. So if we do that, then each one will get 1/10. That uses up 11 of them. So we still have 9 tenths left over. So let's turn those into hundreds. So we have 90 there. That's going to go 8 times. That's 88. So we'll have 2 left over, and we'll turn those into thousandths. So we have 20 thousandths. And that's going to go only 1 time. Uses up 11, 8. So you can see, sorry, not 8, 9. You're going to see that we're repeating the same numbers over and over again. So try it one more time. This is going to be 8 times. We get the 88, and then the process starts over again too. So our remainders over and over again are a 9, 2, 9, 2. And so as that's happening, we're getting the 1, 8, 1, 8. All right, for the following, use a grid to model, a number line to model, and write as a fraction in simplest form. So it says a grid. It's talking about the hundreds grid. So let's just draw a little quick one since I didn't put it in here. So talking about that now, 70% is really 7 of the columns in the 100 grid. So we have 10 columns, 3, 4, 5, 6, 7, 8, 9, a little bit longer. And so we have 7 of them. So there's the 70%. So really, as a fraction, that's 70 out of 100, which is 7 of the tenths. And so on the number line, here's from 0 to 1, and it's breaking up. We can do it as tenths. We don't have to see it as hundreds. So there's 2, 3, 4, 5, 6, 7, 8, 9. Pretend they're all equal. And so 7 tenths would be right about there. That's where 70% should be. Now 3% on the 100 grid, that's 3 out of the 100. So that's just like 3 of the little squares. So imagine all of those squares filled in. We're only talking about those 3 guys. And so then on a number line, that should be teeny tiny. Between 0 and 1, that's like teeny tiny right there. That would be where we would write 3%. So we have the grid, the number line, and we wrote it as a fraction, and it won't simplify. Now 1.5%, that's even smaller. That's only 1 of those little corner guys. And then, oops, we could darken this. and then it's only a half of 1. So it's one whole guy and then a little half. So that's 1.5 out of 100, but really that's 15 out of 1,000. So on our number line, it's even closer. We're saying 0 to 1. If 3% was right here, it's got to be even closer, which is 1.5%. Now, as a fraction, I didn't simplify it, but 15 over 1,000, if we reduce it by, let's say 5, so 1,000 divided by 5 will get us 200, and we get a 3, so that's 3 over 200 reduced. For 16, it wants us to show with the percent bar 30% of 80. So the percent bar is just like we were looking at the fraction bars for our proportions. We can have 100%. So we break this up into 10 equal sections if we want to go by 10%. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Pretend they're all equal. And so it says, what is 30% of 80? So if we're thinking about this as 80 being the whole, if we take those 10 squares and divide them up, or divide the 80 by those 10 squares, each one of those is only going to be 8. So each one of these is really a value of 8. We're talking about it in terms of the 80 being the whole. And so 30%, if this was 10, 20, 30%, we're talking about all that section, which is really 24. As a proportion, we're saying, okay, well, 30 out of 100 is equal to what out of 80? So again, 80 is our whole. We want to know what that little chunk is. So this will say, okay, well then 30 times 80 has to equal 100 times x. That's 2400 equals 100x. Divide by 100, and you can see the 24. Again, we get 24 equals x. All right, for the next one, it says a shirt decreased from $20 to $16. What was the percentage decrease? So we know that the original whole amount was 20, and so we want to know really how it was decreased. So 16 is the new amount, but we want to know what was the little loss there. So it went down by $4. So we want to know what 4 out of 20 really is. And in percents, that means out of 100. So again, I set up the proportion. 20x will have to equal 4 times 100. That's 20x equals 400 divided by 20. We get x is equal to 20. So that's a 20% discount. All right, for 18, 19, 20, these are going on to the real numbers. So if we want to draw a triangle with a hypotenuse of radical 3, if this is radical 3, we showed that this could be 1, and then this could be radical 2. So by Pythagorean theorem, radical 2 squared plus 1 squared, that's 2 plus 1, will equal our hypotenuse squared. So 3 equals c squared. So that means our hypotenuse would be radical 3. For the simplifying number 19, we do not want decimals. What we're looking for is perfect squares we can take out of those radicals. So 72 is really the square root of 36 times 2. So I could write this as radical 36 times radical 2, which is 6 radical 2. For 324, that's a big number. I'm going to try and break this apart because I'm not sure what that is. So if I break this apart, well, I know that 2 goes into 324. That will be 162. And then 162 is 2 and 81. Well, I know 81, that's a perfect square. And then with these two 2's, I can actually rewrite this. This is a perfect square here. Radical 4 times 81. That's going to be radical 4 times radical 81. So 2 times 9, which equals 18. So that means for us that 18 times 18 is really 324, which you can check on your calculator. All right, the last one. Using the squeeze method, we want to find what the square root of 13 is. Well, radical 13 is between two perfect squares we know. We got to think about that. Square root of 9, and then this is 3, and then 4, which would be square root of 16. So it's kind of right in the middle, it feels like, between those two values. So let's try and kind of squeeze that together. So like 3.5, so maybe try 3.5. Let's see what that value is squared. That's about 12.25. So then maybe if we get a little bit closer, like 3.6, let's see, 3.6 squared will be 12.96. So between maybe let's try 6.2, 3.62. If we square that, we're at 13.1. If we look at 3.61 squared, that's at 13.03. So actually, looking at the values, it looks like radical 13 is really right between 3.6 squared and, oh wait, let's see, 13 was, so that's the square root. So we're looking at just 3.6 and 3.61. So radical 13 is about 3.6, which on a calculator, it comes out to be 3.6055. So it's awesome. You just put it right in the middle there.